Good afternoon and welcome to our webinar this afternoon. Before we get started, just some housekeeping. If you have any technical issues, please send a short message in the questions box on the right-hand side of your screen. During the webinar, RSSL would also like to ask you to invite questions using the questions box. And at the end of the webinar, time permitting, we'll try to answer as many of these as possible. Any we don't get around to today, we will answer offline and share them with you along with a copy of today's slides. So today's webinar is setting environmental monitoring frequencies using a risk-based approach. I'm just having a little bit of trouble with my slides. They didn't want to move on, sorry. So my name is Annette Russell, for those of you who haven't attended these before, and I am the sterile and non-sterile microbiology lead at RSSL. I've worked in the commercial team here at RSSL for over 6 years, and my role is to support our clients that require a variety of microbiological testing, from routine microbial limit tests through to more complex environmental monitoring or cleaning validation projects. I'm pleased to announce that we have a 2024 webinar series. For more details of the webinars that you can see in front of you now, please head over to our website where you'll be able to sign up and you'll be able to get more information about what they may contain nearer the time. We also have Tim's regulatory updates available via our website. And if you need any help from any of our technical experts, there is a request information page on there too. For those who are new to RSSL, who are we? So RSSL are a growing CRO supporting clients with a wide range of analytical services. We have been around for over 30 years and are based exclusively in the Reading area. We have 4 separate sites within that Reading base. For those of you who don't know where Reading is, it's about 40 miles west of London and Heathrow Airport, and we have all the excellent rail links and road links that you would expect of a major city. Sorry, town, it's not a city yet. Our 4 sites accommodate over 250 scientists working and supporting clients in 12 different technical areas, of which microbiology is just one of them. And we support clients globally. So we have clients from all around Europe, in the US, and as far away as Singapore and Australia. RSSL's unique offering is that as a relatively compact CRO, we have the capability of site agility to manage complex multidiscipline projects. Furthermore, we are backed by the multi-billion-dollar parent company Mondelez, allowing us to have access to funding to support expansion and growth as the markets we work in grow and diverge as well. The 12 technical areas we specialise in allow us to support a diverse range of biological, microbiological, chemical and physical analytical services across all phases of clinical development through to commercial release. We are exceedingly well placed to support all of the new Annex 1 regulations and are lucky to have a knowledgeable technical team who can advise and support you throughout your manufacturing, be that routine raw material testing, or investigative supports of any issues you may face, such as impurities or foreign particles in your processes, as well as enabling you to comply with the new Annex 1 regulations, such as with the environmental monitoring or disinfectant validations that are now required. So we have the capability of supporting you for your environmental monitoring either by consultancy, so looking at the processes you currently have and advising, or we can do the more routine support such as growing and checking your environmental monitoring plates or IDing any of the isolates that you may have grown on those plates. And quite often we can get your results in 48 hours. Well, that's enough of me. I would like to introduce you to our guest speaker today, Dr. Tim Sandle. I'm sure many of you have heard of Tim and subscribe to his many publications. So Tim has over 25 years of experience of microbiological research and biopharmaceutical processing. Tim is a member of several editorial boards, and he has written over 600 book chapters, peer-reviewed papers and technical articles relating to microbiology. Tim works for a pharmaceutical manufacturer in the UK and also finds time to be a visiting tutor at both the University of Manchester and UCL. So I will now hand you over to Tim.
Okay, thank you very much. Okay, brilliant. Okay, well, thank you, and it's a great pleasure to
Tim,
be.
it's not in presentation mode again. Oh, is it? Okay, sorry. Yeah, no, my mistake. It's just my computer that was playing up.
Okay, that's great. All right, well, welcome everyone. It's great to be back with you, and we've got some exciting subjects to be discussing with you over the course of the year. So this particular webinar is going to be looking at some of the sort of subtleties of environmental monitoring, and this is kind of in keeping with what Annex 1 is asking. So it's asking for a more developed, more risk-based environmental monitoring program. So we're going to be looking at how we can determine how often to monitor. So we know that for aseptic processing, it's fairly clear cut. It's asking for continuous monitoring. But what about the support rooms? What about, even if we're sterile manufacturing in grade C or D areas, or if running a non-sterile facility? How do we come up with frequencies of monitoring that make sense? And then the second thing we're going to be looking at is to do with if we want to remove samples, is there a way that we could systematically remove samples, again using sort of risk-based thinking, to be able to justify to a regulator that we've taken the right sample out and we haven't just done that arbitrarily. Okay, so before we get into the aspect of the monitoring frequencies, I think it's important to pause and consider, what are we trying to do? What can monitoring actually show and tell us? So environmental monitoring, and we've discussed in previous webinars, there are some weaknesses with the methods, but if we put enough together and we look at the trends over time, then environmental monitoring can still be a powerful tool in terms of signaling change. So provided we've got a large enough set of data and we can assess that over a meaningful period of time. And we can make that even more powerful by selecting the right locations within the clean room, and then also having frequencies of monitoring that actually matter. But just again to re-emphasize something that I say every time we talk about environmental monitoring, and that's that monitoring is no substitute for control. So we need to get control first, and also if we've got weak controls, we mustn't use monitoring to cover up weak practices. The other important thing, and again in keeping with what Annex 1 is seeking, is that environmental monitoring needs to be risk-based, and we need to use appropriate risk tools. So for environmental monitoring sample site selection, then a useful risk tool in my mind is the hazard analysis and critical control point, or HACCP approach. And this is because this sort of methodology allows us to look for potential contamination sources as we trace the routes that product takes, the route that people take, the path that equipment takes, and also the way that waste would leave an area. So that can help us with locations and to a degree with the most appropriate methods, and also in terms of helping with the scheduling. It's also important for us to establish alert and action levels, and to kind of map out, where possible, the most suitable types of actions that we should be taken when these limits are exceeded, or we start to see a out of trend situation develop. It's also important that our environmental monitoring program is dynamic, and it's something that we can review and adjust accordingly. So within a clean room, production personnel will sometimes move things around, or during periods of shutdown there may be walls knocked down, rooms reconfigured, there may be new processes, new technologies to develop. And again, Annex 1 is also signalling that we need to be mindful of what happens during maintenance, what happens prior to a shutdown and coming out of a shutdown, and also in our understanding of the frequency and suitability of cleaning and disinfection practices as well. And of course, as with anything in pharmaceuticals, we need to make sure we're appropriately documenting things, and that the people carrying out these important tasks are aware of what they're doing and why they are doing it. Another thing that falls under the general risk framework is the importance of identifying sources of contamination, of identifying points where contamination can be more easily transferred from a lower risk place to the point where it could ingress into product. So we can sort of draw, again, additional information not only about locations and frequencies, but also about how big a sample should we take, what's the duration that we want to monitor for, and what's the most appropriate time that we need to monitor. And also we need to make sure that we are capturing the different vectors by which contamination can be distributed around the clean room. So airborne contamination, okay, a level of airborne contamination may exist, but we are concerned about how the air pattern distributes. Air is an effective vector, and then whether the microbial carrying particles in the airstream could potentially settle onto product or onto product contact components. People, again, with gowning and the way they behave, and then also with water, which is a growth source and a vector, again, of contamination transfer. But let's move on to look more specifically at environmental monitoring frequencies. So how do we set frequencies for the viable monitoring for a non-sterile manufacturing area? Now, by non-sterile manufacturing, I'm referring to those areas outside of direct sterile production. So we'll have sterile facilities with grade C and D areas, and then we're also going to have non-sterile pharmaceuticals. So hopefully some of the information we'll be discussing will be suitable for both types of pharmaceutical manufacturing. And here there's an importance that what we are doing is of sufficient frequency, and what we're doing is sufficient to assess the risk to product. but also at the same time, we want to avoid unnecessarily monitoring when it's not needed. So we're also trying to avoid things that are time consuming, expensive, and ultimately unnecessary. So here we can use risk-based thinking to help us with this task, and we can use a risk framework to help us to select the appropriate criteria. So what we'll be looking at are the key factors that make up a particular production room that might increase or decrease either the possibility of there being microbial contamination, and then also the likelihood that microbial contamination will persist for a period of time or could be deposited into our pharmaceutical product. So the risk-based concepts of severity and probability are important. But because we're looking at a group of clean rooms and we want to set appropriate frequencies, we need a system for ranking those risks. So we need to be able to say that a given room is of a greater risk and therefore might require higher environmental monitoring frequency than another room. And if we're going to group rooms together to try and develop a coherent environmental monitoring program, then we need a process of filtering those risks. So these are parts of ICH Q9 that perhaps are given sometimes less attention. So there's lots of information there about HACCP and FMEA and the kind of tools, but in the later part of that document, it does talk about risk ranking and risk filtering. So we'll be able to look at those types of examples. So what I'm also going to be talking about is kind of based around a case study. So I'll start off talking a little bit abstract and then start to look at the example of an actual clean room. So, and this is an exercise that was undertaken for a relatively large pharmaceutical manufacturing facility. So it included around 180 clean rooms that were classified as grade C and around 50 that were classified as grade D. Now, you may not have a facility that large, but hopefully, again, the examples and the approach taken will be something you can apply to a facility of any size. And then just further with the case study and a little bit of background, the environmental monitoring regime typically consisted of the 4 primary culture-based methods. So we have active or volumetric air sampling, saddle plates, contact plates, and swabs using tryptone soy agar, and then that was subjected to a dual incubation regime. So the aim of the exercise was the application of risk assessment to review the environmental monitoring frequencies based on identified risk factors in each given clean room in relation to the potential for microorganisms to exist, microorganisms to persist, and microorganisms to be transferred into product. So principally we have risk identification, the expression of the hazard, risk ranking, and risk filtering. So the approach taken was to first of all identify these risk factors, and we'll have a look at those in a moment. So what are the things that can either influence microbial presence or microbial survival or even microbial transfer? What's the likelihood that the contamination will occur? And what are the consequences or severity should that contamination occur and exist for a prolonged period of time? So we're looking at multiple factors, so multiple risk factors, and then for each risk factor there are different scenarios that would exist for each one. And these are all aspects of the clean room design or approaches to processing that could pose a risk to the room or to the product. And here we've got the exercise of breaking down each risk factor into as many components as are needed, and then using a scoring system so that we can compare, prioritize and rank individual clean rooms. So leading into that process, by taking these two concepts of severity and probability, I'm going to use a scoring system that's based on low, medium, high for each one. So in relation to severity, it's low if it's unlikely to present a risk to the product, it's medium if it's a low risk, and high if it presents a tangible risk. And then probability, the likelihood that the environment will have a presence of microbial counts, is that again low where contamination events are rare, medium if they're infrequent, and high if they are frequent. And here we can draw upon a lot of environmental monitoring data to help to guide us through that process. So with the risk identification process, there are actually around 10 risk factors that we're going to look at. Once we've kind of gone through those, we then look at a risk ranking. So that's how important are the risks relative to each other, and risk filtering is how we can evaluate these different risks. So to begin with, we need to consider some monitoring frequencies. So these were the frequencies that were selected, which suited the particular production process and have a kind of a degree of criticality. So there are some clean rooms we would wish to monitor on a weekly basis. These are the ones where we need the most direct information about the risks of the product. Others can be done fortnightly or every 2 weeks. Others monthly, and then there's a few very kind of low risk grade D office areas, cupboards and things that probably would meet a 3-monthly monitoring regime. But these are arbitrary. You could run this with daily monitoring if you wish to, or you could increase or decrease those frequencies. It's the important thing is to kind of set out what you think is reasonable, and then the objective is to say, okay, how many clean rooms should really fit into each one of those categories. So the next thing is the scoring system. So with the scoring system, and just a reminder that severity is how bad could it be if microbial contamination was to occur, and the probability is the likelihood of contamination actually occurring. And the score ranges are kind of divided up into approximate 1/3 groupings of the minimum and maximum scores that were possible. And we'll explore that over the next few slides. So with that scoring, the next thing that was done was to establish a risk matrix. So here we're looking at how the concepts of severity and probability interact, and then to explain those relationships further, 3 risk classes we use. So risk class 1, this is represented by the red squares, is designed to capture high severity and high probability events, and that is what could cause considerable product contamination and is also quite likely to happen. Risk class 3, which is represented by the white squares, is low severity and low probability, and then in the middle are the intermediate events as represented by the pale blue squares. And there's a slightly greater weighting towards probability than severity, because if contamination is more likely, then that is potentially the worst situation that could occur. So this is a little bit abstract. It will hopefully become clearer as we work through this model. So the next thing we need to do is identify the risk factors for each clean room, because we're going to have different types of clean rooms used for different purposes throughout grade C, D, or in control not classified environments. And in this particular case study, there were 10 risk factors that were identified. So the first of these is the temperature of the clean room. And this is all about the potential for microorganisms to survive and proliferate. So it's a severity question. What happens if microorganisms survive and proliferate? And here there's a different scoring system that's been used. So with a freezer, most freezing is microstatic or it's microcidal. So it either leads to no microbial growth or it kills microorganisms. And for the general pharmaceutical environment, the types of organisms that we will come across are unlikely in most cases to survive where we have a freezer. In a cold room, generally for most organisms, this is going to be at least microstatic. Now, there's going to be some exception. We will occasionally find cyclotolerant organisms. You may even find cyclophilic organisms. We can gain an understanding of that if we understand what our microorganisms are from our environmental monitoring. So if we do find, say, Pseudomonas fluorescens, that's an organism that is cyclotolerant. But if we're finding Staphylococcus, then that's not really going to be able to proliferate in a cold room. So generally, and in this example, a cold room gets a lower rating. And then the higher ratings are given to warmer areas, maybe where there's heat produced from an autoclave, for example, and then ambient areas, because ambient areas are particularly in tune with the typical contamination that would be shed from a person. So that type of human skin-derived microbiota, the Staphylococci, Micrococci, Coccarea, those sorts of organisms would be able to proliferate under sort of standard ambient conditions for a period of time. The second risk factor that was looked at was whether the area was wet or dry. With that, a wet area always presents a a greater risk because water is this vector and growth source for microorganisms. The drier the area, you're going to get some organisms that will naturally desiccate, and it's also going to reduce that variety or diversity of different microorganisms that could be found. The next risk factor that was examined was whether a room had a drain in it, because drains are quite difficult sometimes to control, particularly if they're damaged. If there's a risk of backflow. There's often a strong contamination build up around the drain, and then within the pipework below the drain, often we're going to get a biofilm forming. So in many cases we can control drains, but drains often add an additional risk that we need to consider, and particularly where we're washing and processing equipment, we're always going to need drains. So there's another risk dimension there, and we've got again a variable scoring: present, not present. The next risk factor related to the type of processing, and in this case whether we've got open processing. So open processing provides a greater opportunity for contamination ingress, even if we try and build barriers around that. Closed processing has a much lower risk, and as long as we've got good integrity, then contamination ingress into the product is going to be very low indeed. And of course, we're going to have some rooms that are not used for processing at all. So we may have an office area within a clean room, for example. The fifth risk factor examined is the duration of activity. So this is on the assumption that the longer a process takes, then the greater likelihood that something could go wrong or a chance contamination event could occur. So here we've got definitions of long, medium and short duration. That's going to vary according to different facilities. In this particular case, short duration was defined as activities less than 30 minutes. Medium duration was up to 2 hours, and long duration was longer than 2 hours. But of course, those times could be different depending upon different situations. The sixth factor, and this is one arguably more in control of the actual facility, but it's the cleaning and disinfection frequencies, and often there will be differences. So, for example, corridors might be done at a different frequency to process rooms, to changing rooms, and so on. So here we've got a less frequent cleaning is afforded a higher score. Standard frequency of cleaning, however we wish to define that, and a higher frequency of cleaning and disinfection. So again, we have the option to introduce weighting in that sense. The seventh risk factor is related to the manufacturing path. So as we move downstream through pharmaceutical manufacturing, related to the distance from final formulation or the distance from finished product. And here the inference is that as closer we get to the end, there are going to be fewer microbiological reduction steps. And when we move upstream, we're going to have more microbiological reduction steps. So we may have points where we're adding antimicrobial materials, we might be using filtration, we'd be using different processes that could dilute or contain contamination better, and our chances of doing something become fewer and fewer as we get towards the very end of the process. The eighth risk factor related to the number of people within the clean room. And here the inference is that the more people in the room, then the greater the likelihood that contamination could occur, given that people under most reviews come out as the greatest source of contamination within the clean room. So we can define different occupancy levels, and this may also be related to room size, that there may be other variables that we wish to factor in. The ninth risk factor is equipment, and here there's assumption that where equipment is mobile, so it's moved from room to room, or it might be taken from the clean room to a washing area and moved back in, that contains more variables, so that equipment is potentially at a greater risk compared with equipment that is fixed within the actual clean room. And then our final risk factor is the environmental monitoring. So we're looking at the environmental monitoring trends, so over a 1-year period. And then this is something that could be subject to annual review, and it may eventually affect the frequency of monitoring itself. But you know, if a room's got a really good EM history and it's on the cusp, then it might be able to move into a lower risk category. So it's a good idea to look at environmental monitoring data and to draw this across all of the different measures that we have, and not only in terms of microbial counts, but also frequency of, say, alert and action level excursions, and also in terms of the types of microorganisms that are recovered. So if we get an area where we're having higher levels of, say, spore forming organisms, that can be as equally bad as counts several magnitudes above the action level. Another step, another consideration in this risk approach was the detection methods as well. So this is a way of saying, okay, well, given the activities within the clean room, what information do we have that helps to inform and tell us whether or not we have a problem? So if all we have at our disposal is our environmental monitoring, then that's what, in this case, I've classed as a low detection method. If we have our environmental monitoring plus we have the ability to, you know, there's a manufacturing stage where we can draw an intermediate sample for bioburden or endotoxin determination, then I've classed that as medium detection. And then if we also have the ability to take samples of water, or we can test things going into product like buffers and things as well, then we have a lot more information if we can do that, plus intermediate bioburden, plus the environmental monitoring. So we have a slightly higher detection of our perceived level of risk. So that's all the different risk factors. So what I proceeded to do was to take each one of the clean rooms and score it against these 10 different risk factors, and you'd have seen that those risk factors were grouped into either severity or probability or both, and this allows us to produce a score for both of those factors, and we can return to our risk matrix. So if we revisit this diagram that I showed earlier, we have three choices for severity, and we have three choices for probability. So severity, how bad would contamination be? Should it be there? Probability, how likely is contamination to be there. So we can start to place every individual clean room within one of those squares and give it a risk class, and we can then start to transition, as I'll show you in a moment. We transition those risk classes into monitoring frequencies. So in general, risk class 1 is capturing those high severity, high probability events. Risk class 3 is capturing the low severity, low probability events. And risk class 2 is for that sort of medium area. But we also need to consider our detection methods as well, because the more ways we have of detecting contamination, then the greater confidence we can have as well. So what this diagram is doing here, so it's the second step with the risk matrix. But here we have on the left-hand side, we have those 3 risk classes, 1, 2, 3. And along the top, we have our 3 different detection methods. So we have low, where we've just got environmental monitoring, medium, where we have environmental monitoring and an in-process sample measure, be that bioburden or endotoxin, and then higher if we can also throw in either assessments of water, assessments of buffers, and so on. So we go from one risk filter and then use the information from that to go to our second risk filter. And then what we can also do is transpose on these outcomes the monitoring frequencies that we were looking at. So this was the weekly, fortnightly, monthly, and 3-monthly monitoring outcomes. So these are the things that I coded as CV1 for weekly, CV2 for fortnightly, CV3 for monthly, and CV4 for 3-monthly. And you know, so before, you can use different frequencies. This is just the concept of that risk matrix approach. And then, so we can take each clean room through and come up with a monitoring frequency and grouping similar rooms together that is based on a proper assessment of the likelihood and probability of contamination. So that's a little bit abstract. So let's take a worked example. So if we take a clean room, and just for the sake of argument, we call this room number 100, and it's a grade D room. And in this grade D room, there are some chemicals that are being prepared. So we need to score the room based on the 10 risk factors that we've looked at. So with this room 100, it's an ambient room, so it's at room temperature. So that from our previous thing we looked at would get a score of 3 points in terms of its severity. It's a dry area, so it gets a score of 1. There's no drain present, a score of 0. It's not directly used for handling product, so scores 0, but it is used for a long period of time. This chemical step takes quite a long time, so we score it as 3. And because it's right at the start of the process, its kind of current cleaning and disinfection schedule isn't particularly high, so it also scores 3. It's right at the start of the process, so it's more than 3 steps removed from final formulation. That scores 1. Not many people are required, so it has low occupancy. It scores 1. The equipment never leaves the room, So again, it scores on the lower side of 1, and it has a relatively good environmental monitoring history. So we end up with our 2 scores, a severity of 8 and a probability of 9. So we need to go back to our first risk filter. So we can take this room 100 and we can position it on our matrix, and it falls slap bang in the middle, and this gives it a risk class of 2. And then we need to say, okay, what do we have in terms of detection? Well, in this particular case, we have the environmental monitoring in the room, and we also have the ability to take a sample of the chemical buffer that's being prepared, so we can take an in-process sample. So knowing that it's risk class 2 and it's a medium level of detection, gives us what we need for when we move over to the second risk filter. So it's risk class 2 and it's medium detection. So again, we position the room as 100 in the middle of our diagram. And then if we transpose our monitoring frequencies, so we're back to our coding of CV 1, 2, 3, and 4, 1 being weekly, 2 being fortnightly, 3 being monthly, and 4 being every 3 months. In this particular example, our room 100 comes out as CV3, so it's a room that on the schema we've constructed we would monitor on a monthly basis, and we would then start to group similar rooms around this, and dissimilar rooms would be at different ends of the scale. So the kind of outcomes that emerged from this are that the lower frequencies of monitoring things like consumable storerooms and cold rooms, medium frequencies of things like changing rooms and equipment wash bays, higher frequencies are for corridors where there's a lot of people activity, and the highest frequencies where we've got open processing. And in a sense, you can start to sense check this, and you could argue that this is just common sense, and these are the kind of groupings that you may have come up with anyway. But what you can do through a similar approach to this is to demonstrate to a regulator that you've applied an understanding of scientific principles using a risk methodology. So there's a degree of sort of structuring and so on that we can use here. Okay, so we're just going to move on very quickly to the second part of the presentation. This will be quite short, but this is about reducing environmental monitoring samples. So we have a clean room. This example is a grade D clean room with 4 settle plates taken in it, and we wish to remove one of those samples. So to my mind, one of the ways that we can do this is to produce a histogram of the data that we get. So in this particular case, the vast majority of the results are giving us a 0 count. We're getting a few at 1, a few at 2, a few at 3, a few at 5, and so on. So And the sample that we think, well, we probably doesn't really tell us much. It's in the corner of the room. It's sample number 4. What we can do is we can go back to our data. We can remodel it by having taken that sample out and see what we get in terms of the histogram. And in this particular case, it looks like our histogram is broadly similar. And we can assess that by having both of our histograms side by side. And if we wanted to, we could run some other supporting statistics, but generally as a visual impact, taking our particular sample out, reducing an excessive sample has not altered the distribution of the environmental monitoring from that room. So we can start together to put together a justification. Of course, we want to make sure all the other variables are in control. So we're still doing the same level of maintenance calibration, we're still doing the same level of cleaning, that we still have our environmental monitoring risk assessments. And it's important that we do that, because if we have flawed risk assessments, if we've got poor data inputs, or if our thinking is unclear, then we will end up with poor outputs. So just some general advice is always to think holistically, think how areas are connected up together, to be driven by our data to actually understand what is going on. And also to understand that the environmental monitoring methods are weak, therefore we need a lot of data, and we need trends over time before we should embark on these types of practices. Okay, so that brings the webinar, my presentation part to an end, and I'll pass you back to Annette.
Apologies, my microphone was on mute. So thank you for that, Tim. We have had a few questions. We haven't got much time to answer them, so I'll try and pick relatively simple ones. So we've had one from Nilesh, and he said, in many industries there's a practice of incubation of 20 to 25 degrees for 3 days, followed by 30 to 35 degrees for 2 days, and they're wondering, is this the correct method?
Okay, so everything's going to vary a little bit according to the facility and the type of environmental monitoring, and it's always recommended that you kind of run a study. However, in theory, a lower incubation is preferable, because some fungi are very sensitive to a higher incubation first. So a low to a high step is generally preferable. But that is an interesting point, and it's an interesting type of study, and that's probably something that might make a good future webinar topic.
And then I've got a question from Taran, who's asking, how often should risk assessments be revised?
Again, I think it depends on the size and the complexity of the facility. But so the important thing is risk assessments don't sit on the shelf and gather dust. They are dynamic. So often the change control mechanism can be a good one to flag the need to review. But even if nothing appears to have been changed, then to look at these things at least every 2 or 3 years would be important.
And from Emily, can increased cleaning lead to a reduction in monitoring frequencies?
I think it can, and I think in the model that I put across, it's one of those things that you can redo it. You could look at different cleaning frequencies and see if that has an impact. And conversely, if you don't have the resources to always clean everything at a certain level, you can also increase monitoring to kind of understand whether that is having a detrimental impact. So it is possible, but it is just one of many factors that needs to be considered.
Okay, and I think this will be our last question from Vishwas. Is it okay to expose settle plates continuously instead of active air monitoring during aseptic filling operations?
I think you need to do both because the settle plate and the active air, although they're both types of air samples, are seeking to do different things. So the active air sample is really important for telling you how many of the particles within that contained space are likely to be microbial carrying. But the saddle plate, if it's in the right position, and you've kind of made reference to your smoke studies, will give you an idea of what the rate of deposition is and what's the likelihood of one of those particles actually ending up in your product.
Okay, well that's all we've got time for at the moment. So thank you, Tim, and thank you for everybody attending the webinar. I hope you found it useful, and we appreciate the questions you've asked. If we didn't answer your particular question during our Q&A session, I'll forward them all on to Tim. And as I mentioned at the start, we'll circulate these along with a copy of the slides in about a week's time. If you wish to catch up with any of our previous webinars, please do go to our web page. You can see the web address on the slide now, where you can download them. And if you want to read Tim's blog or regulatory update, again, this is also on our website, or keep an eye on our social media posts, as are the future webinars. And as you'll see on this slide, with the email that comes out with the slides, if you keep your eye out, we're going to do a microbial identification offer. So thank you for attending the webinar today, and we look forward to seeing you on the next one in May. Thank you.